Okay, we've been building toward this a while now. Now let's get going. Kirchhoff, like you mean it. Okay, so I've got two examples here. I guess they're always kind of similar because it's the same sort of analysis that we're trying to learn. It's a sort of a method that we want to learn, and hopefully by the end of two examples, you'll sort of start to get the dance steps into your bones a little bit. So I've written the steps up here for reference, and the first thing always is to draw the current. Draw arrows representing current. So looking at this circuit, how many branches do you see? How many different flows are there? How many different currents are there? Well, you got a branch that goes from here to here. That's all going to be the same current going through that pipe. You also have another branch just from here to here, right? So that's going to be its own flow. And then you also have another branch that starts here and goes all the way around like this. 3 branches, 3 branch currents. We're going to have 3 currents that we have to solve for, 3 different currents. And we don't have any current sources saying, hey, it's 3 amps over here. We have no idea. So what I'm going to do is I always go to the big battery first, and I figure, the big battery's probably going to get its way. No guarantee, but probably. And I'm going to say, I have no idea what the current is. It's X. So I got X amps going through the 28-volt battery. Now remember what I was saying. This is all the same branch. This is all the same flow. This also has to be X amps coming through this resistor because, again, it's all the same pipe. It's all the same tube. Okay, now things change when you get to a junction. So I got X coming around the corner. This is still X coming around the corner. But then I get to a junction. Okay, now things can change. Or they have to change, really. So let's see now here. What am I looking at? I'm looking at 2 more batteries, and looks like they both want to go down, but they can't. We can't have all of these batteries going into the junction. So we're going to have to, you know what, who cares? I'm just going to guess that the current's going this way. Sure. Going through the 2 ohms. I mean, it could be coming down, but I don't know. So you have to pick one direction, right? So I'm just going to say, yeah, maybe it's going that way, and maybe it's going up like this. So the current's splitting into 2 like this. So X amps are coming in, and they're dividing. Some of it goes this way, some of it goes this way. Now, if we had exactly equal resistances on both sides, then half would go one way, half would go the other. But we don't have exactly equals resistances on each side. So we have to say, okay, so this is splitting up somehow. What are we going to call this one? I don't know. Notice we need another we need another letter. So I'm going to have to call it Y because we have no other clue. Now this one, you could call it Z, but that's just temporary because do the in out here. What goes in must go out. Coming in is X. Going out is Y plus Z. Right? Coming into this junction is the X amps. That's the in side. Going out of this junction is a Y plus a Z. I put that on the out side. But then notice you can actually kind of rearrange this equation and say, oh, so if I subtract Y on both sides, see, Z is the same as X minus Y. So I don't have to label this with the Z. In fact, better off not doing that because then I have an extra thing to solve for. We don't want an extra thing to solve for if we can help it. But it looks like we are going to have to solve for at least 2 different currents. We have to solve for the X, we have to solve for the Y. Once we have X and Y, of course, we can figure out what that is. So we have to solve for the 2 currents. Okay, so let me get this stuff, well, I guess I know what I'll do. I'll just shrink it down. Boy, it's kind of nice to be able to, hey, I said, what? Okay, shrink it down and kind of move it out of the way. Okay, cool. So getting back to my currents, right? So I had the Y amps coming up this way. Of course, it's going to be Y amps through that as well because this is all the same current in this branch. And then this is all the same current in this branch. Tells me that I've got the same X minus Y that's flowing here must be flowing here. Okay. This thing is getting jittery. So I guess I've done that. I've labeled all my branch currents. There's no other currents to label. Branch currents, done. Label arrows. Okay, label arrows using Kirchhoff's current law at any junction. I guess I did that at the same time, didn't I? Huh. Here I am combining steps together. So we did 1 and 2 at the same time already. We drew the arrows, we guessed which way it was going, and we labeled the arrows with an X, a Y, and that one's an X minus Y. So what is next then? Well, what's next is step 3, resistors minus where your mouth is, right? Remember this idea? So looking only at the current through this resistor, I would say, okay, the current's coming in the top. That's where the minus goes for that resistor. Looking only at the way the current is drawn for this resistor, I say the current's coming in the bottom. Minus goes there. Why do I say that's where your mouth is? Because if you were blowing through the straw, you'd have to put your mouth on this side in order to blow through the straw this side, right? So that's all that means. It's meant to be a silly idea that actually works. Here's another resistor. Looking only at the way I've drawn the arrow, it says, oh, the arrow's coming in on the left side. Well, if the arrow's coming in on the left side, that's where the minus goes. That's where the mouth goes, right there. That's how you do the resistors. Sources, you put the minus where it wants to come out. Now, actually, with these things, with voltage sources, they always they put the plus stamp right on it for you, which means that's the minus stamp. They put this plus stamp right on it for you, which means that's the minus stamp. They put the plus stamp right on it for you, which means that's the minus stamp. So I got all my plus minuses done. That's all the setup phase, the decoration phase. Now comes walking around in circles and solving equations. That's where the real work is. Of course, you have to set it up right, or your work's going to be all for naught, which is a bummer. But I think we can start walking in circles. Now I've got a choice of circles. I can walk around this loop. I can walk around this loop. I can walk around the outside. It does not matter. You'll get 3 different equations. But in the end, the solutions will all work out. The algebra knows what's going on. It keeps track of what's going on. So I got to walk a loop. Okay, I'm going to put Ant-Man here. Here's Ant-Man. And it doesn't matter if I have him walk around clockwise or if I have him walk around counterclockwise. The equation will look slightly different, but it'll have the same solutions in the end. You just got to trust me on that. So you don't have to fret too much about, well, which way should I go and where should I start and all this stuff. Just walk in a circle. That's all you got to do. So I think I'm in the mood to go clockwise. Here comes Ant-Man. Oh, he sees a plus on the way in. Plus, and you always go for the volts, right? And it says 10 volts, so it is 10 volts. It's the voltage law. You always go for the volts. Pop out the other side. Come around, come around. Ooh, I see a plus on the way in. Plus. And then I'm looking for volts, right? And that says 2 ohms. That doesn't say 2 volts. That's not volts, that's amps. That's a current. But if you multiply those together, you get volts. That's called Ohm's law. If you multiply the resistance times the current, you get volts. So the volts there is plus 2 parentheses X minus Y. Okay, now Ant-Man pops out to the other side. He takes a corner, he starts coming up, he sees a minus on the way in, minus. And again, the volts here, well, that's not volts, but if I multiply them, it's volts. Cool. Come on, Ant-Man, keep going. He comes out here. Now he sees a minus on the way in. Now this is a battery. It's 8 volts. Notice I don't have to say 8Y or anything weird, because it is 8 volts. It's a battery. It's 8 volts. Put an 8 and be done with it. Okay, so Ant-Man comes out. Oh, I'm back where I started. Equals 0. Da, 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 da. And that's our first equation. Except it's kind of a mess, so let's clean it up. Let's get rid of those parentheses, right? Remember this distribute idea. So plus a 2x, minus a 2y, and then I've got minus a 4y, minus an 8 equals 0. All of these terms are all on the same side, so I can just kind of rearrange them, combine like terms. I like to put the x first, so there it is. I like to put the y's next. There's 2 of them. They should combine. They're like terms. They go together. Minus 2y minus 4y is minus 6y. Cool. And then the numbers. I get a 10. Take away 8 is a 2. Cool. And if I put this in standard form, I'd have the 2x here. I'd have the 6y here. And I would actually subtract 2 on both sides. And that's my equation, the first. That's my first equation. Looks cool. I want to make a little more room over here, so I'm going to slide that back a bit. Here we go. All right, let's get a different color, do a different equation. Why do I need a different equation? Because that's got an x and a y. I can't solve for either one until I know what the other one is, right? So I need to walk around again. So now you see the point of the last homework, right? 2 equations, 2 unknowns. That's kind of what we're heading for here, folks. So let's have Ant Woman, Ant Girl, Ant Boy, whatever. Ant Lady. How's that sound? We'll have Ant. Oh wait, isn't she like some kind of wasp or something? Well, anyway, Ant Lady. She's going to walk in a loop. She's going to walk in a different loop. And again, it does not matter. Come on, you. It does not matter if she goes around the whole outside. She can do that if she likes, or she can go around this side. She can do that if she likes. Right? It's a free country for a while more anyway, so she can do that. I'm going to have her do the left loop just because. So she's going to walk, 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 take a turn, and then you can see a plus on the way in. Start with the plus. You want volts? We got volts. It's 8 volts. Cool. That's an 8. 8 volts. Pop out the other side. Oh, I see a plus on the way in. Plus. I want volts. And that's not volts. And that's not volts. But if I multiply them, it's volts. So that's a plus 4y. Come out the other side. Do, 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 do. Come around here. Do, 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 do. Come around here. Oh, I see a minus on the way in. And I want the volts. We got the volts. It's 28 volts. Cool. Pop out here. I see a plus on the way in. That's not volts. That's not volts. But if I multiply them, it's volts. So I have a plus 7x. And then I get back to where I started. And you finish your equation by saying, I'm back where I started. Honey, I'm home. Equals 0. This equation we should clean up a little bit. I like to put my x term first. So the 7x I'm going to put first. I only have the one y term, plus 4y. It goes next. These will combine, of course. They're like terms. They're both constant terms or numbers. 8 minus 28 is a negative 20, right? Yep, yep, yep. And then actually, to get the official standard form, I want to add the 20 on both sides. And look at this. There we go. That looks good. And that's my second equation. We're moving now, folks. Now, here's an equation that has an x and a y in it. Here's an equation that has an x and a y in it. Neither one of these equations can be solved alone, but you put them together. You put them together and you can make some progress. So I'm going to sneak this equation right underneath this one. 2x minus 6y equals a negative 2. Again, that's just my equation 1. And now we want to think in terms of adding these two equations together to make something go away. The problem is if we add them now, nothing goes away because, 7x plus 2x is a 9x. That doesn't go away. 4y minus 6y is a negative 2y. That doesn't go away. I need something to go away. So what we got to do is we got to fudge this a little bit. So think kind of like when you're doing common denominators and fractions. If I had sevenths and halves, I could make 14ths, right? That would be my common denominator. I could do that. Or I have a 4, I have a 6, I can make them both into 12s. That sounds better. Let's make them both into 12s. So what I'm going to do then is I'm going to take this equation here, and let's see, I want to make this 4 into a 12. I'm going to have to multiply this whole equation by 3. The whole equation, by the way. And then this equation, in order to make that into a 12, that 6y into 12, I'm going to have to multiply that equation by 2. And notice as a bonus, 3 times 4y is a positive 12y. 2 times this is a negative 12y. They really will go away upon adding. Awesome city. So let's get down here and start some adding. So my new equations, after I multiply, will be, let's see, 3 times 7. 21x plus 12y equals 60. Make sure you multiply all the way across. 2 times 2, 4x minus 12y. 2 times negative 2 is negative 4. Again, all the way across. Now I can add my like terms. 21 and 4 is a 25x. The y's go away. 60 take away 4 is a 56. Looking at the x, you say, oh, I'm going to have to divide both sides by 25 here. right? So you take your 56, you divide by 25, and you know, you'll get yeah, you'll get 2.24. We've got an answer today. We've got an answer today. X is 2.24. What I can do with this answer is I can come back up here and I can say, hey, where's X amps? It's right there. It goes through the 28 volt. So coming through the 28 volt is 2.24 amps. That's also what's going through the 7 ohm. So what going through the 7 ohm is 2.24 amps. And unfortunately, that's it. Those are my two currents there. Now, what I can do next is, what's a good color? Let's go back to blue. What I can do next is I can solve for y. So solve for y. I can plug into either one of these equations. I'll just plug into equation 1, I guess, because it's right there looking at me. Oh, wait a second. I know what x is. So what I'm going to do is I'm going to plug x in right there. So 2 times x is 2.24 minus 6y equals a negative 2. 2 times this is a 4.48 minus a 6y equals a negative 2. You subtract this on both sides. You end up with a negative 6y equals a negative 6.48. You divide both sides. Whoops! You divide both sides by the negative 6. So that the negative 6 will cancel off, and you end up with y equals, sneak this in here, looks like a positive, negative by negative is positive, 1.08. That's my y, 1.08. I got y coming through the 4 ohms. That's 1.08. That's what I said, right? Yeah, that's what I said. I got y going through the 8 volts. That's 1.08. And while I'm at it, I can go ahead and fill this in. Through the 2 ohm resistor, we've got, well, you're supposed to go x minus y. So that's going to be the 2.24 minus the 1.08, which is going to be a 1.16. And that's the same coming through the 10 volt battery, 1.16. We've got all of our branch currents solved. Now we want to get some volts. Finish up with some volts. The easiest volts to do are the sources. A 28 volt source has 28 volts. An 8 volt source has 8 volts. A 10 volt source has 10 volts. That's just the way those work. For the resistors, remember that's not volts, that's not volts, but if you multiply them together, you get volts. So that's 15.68 volts. Multiply this times this, you get 4.32 volts. This times this, you get 2.32 volts. Interesting. All solved up. We've got everything. We've got every piece of voltage information, every piece of current information you could ever want. All solved. So, being able to solve 2 equations with 2 unknowns is part of your skill that you need to develop here. So let's, I suppose I could just kind of, yeah, we could ignore all this stuff, right? Yeah, we'll just ignore all this stuff. Just kind of make a border here between our 2 problems. Let's do another problem. What do we got here? Well, we got 2 sources. This is a voltage source. This is a current source. So remember, the voltage source is going to force 3 volts. The current source is going to force 2 amps. Now, the first thing I want to do is I want to pick a different color. The first thing I want to do is I want to start drawing some currents here. Well, I know that this is 2 amps. This branch is 2 amps, right? Because it has a 2 amp source. That's got to be 2 amps. I don't even have to label it, really. But I got a battery over here, which is probably pumping juice this way. I could be wrong. But I'm going to guess it wants to pump out the negative terminal. And we don't know what that is. It can't be 2 amps. It's in a different branch there. So I'm going to have to call it X amps, I guess. Now, there's a certain art to labeling currents. And, you know, I'm not just going to put like a Y here randomly. What I'm going to do is I'm going to sort of start following my currents around and label as I go. So you see that X that I just put there? Well, it's still X when you get over here, right? we're getting to a junction here, folks. And then notice at this junction, I've got a current here that's going up. Well, it's 2. I don't really have to, well, I'll just put it right there, 2. It's 2 amps going up. Now, what happens over here? Well, I don't know, but I'm going to maybe guess that it just kind of goes like this. I can do that. So the question is, I'm going to put a Y just for a second, but do I really need to label it with a Y? Let's see now here. Doing the in equals out on this junction. Coming in is just an X. Going out is a Y plus 2. So notice what Y is. If I subtract 2 on both sides, it says, oh, I don't have to use a Y. I can just label that as an X minus 2. So X comes in, 2 goes out, this is what's left over. X minus 2 is what's left over. It goes this way. That's going to be the same here because it's all the same branch, and it's going to be the same coming in over here because it's all the same branch. So you just start following your currents around. Now what? Now I'm over here at this junction. And what's going to happen? Well, I don't really know. So I'm just going to guess that the current splits and some goes to the left and some goes to the right. It's a good enough guess. Remember, if I'm wrong about the direction, I'll just get a negative answer, and I ain't scared of no negative answer. So I'll just be fearless. I'm going to say that current splits. Cool. Now, what's this one? Y. Got to call it something. Notice I'm not going to be able to do in equals out to figure out what that is, or to figure out what Y is, because I don't know what that is. So that means I'm stuck with the Y, is what I'm trying to say. That's going to have to be a Y. How about we call that a Z then? Okay, I'm calling it a Z, but just for the moment, because what I want to do now is I want to do the balance, in equals out, and see if I can, instead of using Z, maybe I can use something else. So coming in is the X minus 2. Going out is the Y and the Z. So actually, yeah, look, I can get Z by itself, subtract Y on both sides. Z is going to be the same as, let's get this out of here, Z is going to be the same as X minus 2 minus Y. So actually, it's a big label, but I can use that instead of Z. I can say, you know what that really is? That's X minus 2 minus Y. That's what that really is. Let's get this a little bit shrunken, and well, let's get this a little bit short. Come on, man. Let's just move it then. Okay. Now, are we missing any currents? Well, actually, we've got something coming, got to go through there, right? So I think what I'll do is I'll follow this flow down and this flow up, and well, they have to come together and go that way, right? You get 2 flows coming in, something's going to have to go out. So, what is that? Again, Y comes in, 2 comes in. The Y and the 2 have to add together to go out. I mean, you could, of course, call it the Z and do the same thing as we did over here. You could say, well, coming in as a Y, coming in as a 2, going out as a Z. And then very quickly you say, oh, so I guess Z is just Y plus 2. So I'll label it with a Y plus 2. Well, I guess labeling those currents was a little bit more involved than usual, huh? So you might want to like go back and do that again before you get too far into the problem. Go back and just kind of make sure that every step makes sense. Again, if you were doing this yourself from scratch, you might have labeled things differently. For all I know, you put X, you know, somewhere. Maybe you made that your X over in through the 6 ohm or something. I mean, who knows? But however you label it, in the end, we should get the same solutions. So notice I always do steps 1 and 2 at the same time. Coming up next is putting the minuses where your mouth is on the resistors. Mouth is there. My mouth is there. My mouth is there. And that's, oh, here's a resistor. My mouth is there. So I got all my minuses, pluses for my resistors. For the sources, put the minus where it wants to come out. Actually, with the voltage source, they outright tell you where the plus is, so you can't get that one wrong. But for this one, you have to say the minus is here. We don't know you know, they didn't tell us that, but this is the way it wants to flow. It wants to flow up. It's a source. Put the minus where it wants to come out. Okay. And I guess the plus would be on this side. And another thing we can do while we're at it, remember the volts across this thing is who knows what. We don't know. So notice, like with this voltage source, hey, I know the volts, but I don't know the current. And then with this, hey, I know the current, but I don't know the volts. See how they're just kind of like mirror images of each other? So I like to put that script red V there to remind me that there's a voltage there, and I have no clue what it is. So I'm just going to use a red V to stand for that at the moment. And we've just done step 3. Now comes the part where you try to solve stuff. You solve stuff by getting equations going, and you get equations going by walking in circles like Ant-Man. So what we've got to do then is we got to start walking in circles. Okay, so let me get some green action going. Now the tip I have is stay away from that at first. Stay away from current source until have other things solved, I guess. In other words, I don't want to walk through that just yet, because if I do, I'm going to have not only x's and y's, but I'm going to have this v here, and I don't know what that is either. It'll be like an extra variable to solve for, so I don't want to deal with that. So I'm not going to walk through that just yet. So what other choices have I got? Well, I could walk around this loop, of course, in a circle. That wouldn't be so bad. I suppose I could walk around this loop, or going around all the way around the outside. That would work, right? Avoiding the current source. If you want to get fancy, you could also go like this. Down, over, and around like this. There's no reason you can't. That's a closed loop. It works for me. But let's see. How should I do this? I think what I'm going to do for my first tour, I'm going to have Ant-Man start here. And the first thing I'm going to have him do is I'm going to have him walk all the way around the outside. It's going to walk all the way around the outside. All the way around like that. So, what's he see? Walk, 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 walk. He sees a plus on the way in. Grab the volts. It's 3 volts. Cool. Not much happening here. Oh, there's a minus on the way in. What's the volts? Again, that's not volts, that's not volts. But if you multiply them together, it's volts. Comes out the other side. Comes down here. Oh, there's a minus on the way in. That's not volts, that's not volts, but if you multiply them together, you get volts. He comes out the other side, he's back where he started, equals 0. All right, there's our first equation. Let's clean it up though. So distributing my negative 7x, and remember negative times negative is plus 14. Distribute here, minus 6x, minus times minus is a plus 12, minus times minus is a plus 6y. That all equals 0. I'd like to put my x terms first. These combined, they're on the same side of the equation. I can just combine them together. Negative 13x. Y terms, I've only got the one y term, 6y. It takes care of that. And now I got to put my numbers together. I got a 3 plus 14 is 17, plus 12 is 29. That equals 0. And to get it into real standard form, my last thing is to subtract 29 on both sides. And here we go. That's my equation 1. Nifty difty. Now let's walk a different loop and get an equation 2. I'll have Ant-Man start at the same place, but this time I'm going to have him go around that way. Have him go around the inner loop. So let's see now here. The first thing he's going to see, first thing he's going to do is he's going to erase that. First thing he's going to see this plus on the way in. That's not volts. That's not volts, but you multiply them together and it's volts. So that's a 5 times a y plus 2. Walk, 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 walk. I see a plus on the way in. right there. I have to multiply the 4 times the y to get volts. Walk, 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 walk. Come over here. I see a minus on the way in. I have to multiply the 6 times the x minus 2 minus y to get volts. And I'm back where I started, equals 0. So now we clean this one up. Distributing 5y plus 10 plus 4y minus 6x plus 12 plus 6y. That all equals 0. Grab all my x terms. There's only one of them. Negative 6x. Grab all my y terms. Put them together. 5 and 4 is 9, plus 6 is 15. And then my constants, plus 10, plus 12 is a plus 22. And just to tidy this up a little bit more, I'll actually subtract the 22 on both sides. I got the x term, I got the y term, I got equals the constant. Cool! I've got 2 equations with 2 unknowns. So, what do you say we solve them? Good thing I can get more paper down here, right? Solving time. I'm going to put my 2 equations, one on top of the other, and just get a look at them here. Negative 13x plus 6y equals negative 29. That was the first equation. Negative 6x plus 15y equals a negative 22. That's the second equation. Now remember, our strategy is to add the equations and have something go away. If I add these, of course, they're not going to go away. What could I use for a common denominator? 6 and 13. The common denominator is 6 and 13. I think you'd have to go 6 times 13, which is like 78. Eesh. Or look at the y terms. We got a 15 and a 6. Hey, we could turn those both into 30s. Let's do that. We'll turn those both into 30s. So what I'm going to do then is I'm going to take this top equation, and in order to make that 6 into a 30, I'll use a 5. In order to make this 15 into a 30, I'll use a 2. Now remember also, I need one of these to be negative, a negative 30y. So I'm going to make that a negative 2. So what do I got here? 5 times negative 13 is negative 65x. 5 times 6y is plus 30y equals 5 times negative 29 is negative 145. On the bottom, negative 2 times negative 6 is a positive 12x. Negative 2 times this is a negative 30y. Negative 2 times this is a positive 44. Add my equations. A negative 65 plus 12 is a negative, I want to say 53. Did I do that right? I think so. The y's go away. Negative 145, add 144, and I believe you've got negative 101, don't you? Because it's kind of like a subtraction. Yeah, okay. The x has a negative 53 coefficient. You want to cancel off the coefficient. You want to stick a negative 53 underneath both sides. And when you actually push buttons, you've got negative by negative is positive. You've got 101 divided by a 53 SD button. I'm going to go to 3 sig fig, or 3 decimal places actually. 1.906. And that sounds familiar. That feels right in my bones. I think I've solved this before. At least 8 times actually. So yeah, that seems about right. 1.906. Cool. And I could start filling in some answers now. Where is the current equal to 1.906? The current is equal to 1.906 here, through the 3 volt. So through the 3 volt, I got 1.906 amps. That's a bit of a shame. That's the only current I've got right now. Looks like I'll have to solve for y. Just going to have to do it. So stick this into any one of the equations. I'm going to put it into equation 1, which was, that's equation 1. So let's see now here. Man, oh man, okay. I got negative 13 times x, which is a 1.906, plus a 6y equals a negative 29. So what is that? Negative 13 times a 1.906 is a negative 24.778 plus a 6y equals a negative 29. So you have to add this on both sides. That gives you a 6y on the left, and this gives me a what now? This gives me a negative 4.222. Lastly, shove the 6 underneath both sides so it cancels off the y. So I take that negative 4.222, divide it by 6, and I'm getting an answer of negative 0.704. Right? Negative 0.704. So you know what? Negative means the arrow's backwards. La-di-da. Okay, so I'm going to come back up to here. Where's my y? My y is here. It's going through the 4 ohm. So going through the 4 ohm is negative 0.704. Put the negative in the box because it's part of your answer. If I look at the negative 0.704, I'll know, okay, so that arrow's backwards. But don't put positive because it'll say, oh, he's got the current drawn the wrong way because he said it was going that way, but it doesn't. It goes the other way. So if you put the negative, it's like, yes, I said it goes the other way. I said it was negative. Okay, so you got the y there. Okay, we can figure out this current. It's a y plus 2 going through the 5 ohm. So this is a y plus 2. By the way, this was x. Sometimes it's handy to kind of do this. This is x, this is y plus 2. So y plus 2, you take the negative 0.704 and you add 2 to it, and you end up with a 1.296. What's going through the 6 ohm resistor? X minus 2 minus y. Oh boy. So I take my x, which is 1.906, I subtract 2, and then I subtract a negative 0.704. Again, use the negative, and end up with a 0.610 actually. These are all some interesting currents we got going here. By the way, the 2 amp source has 2 amps. It has to. That's what it does. That's its reason for being, is to make 2 amps. The 7 ohm resistor has how many? It has an x minus 2. So x minus 2 is the current. X is this. If you subtract 2, oh boy, that's also negative, huh? 1.906 minus 2 is a negative 0.094. And there's all my currents. Cool. You want to get some voltages going? Well, the 3 volt source is 3 volts. I got that one. Here I'd have to multiply for a resistor. Again, you go this times this. 6 times the 0.610 is 3.66 volts here. 5 times the 1.296. We got 6.48 volts here. 4 times the negative 0.704. We got a negative 2.816 volts here. Remember, this is a special thing to solve for, so we have to skip that for now. But for the 7 ohm, I could take the 0.094 negative times it by 7. I really can. And I get a negative 0.658. Oh, look at that. We were so close to being done. But we're not done because we need to solve for that voltage. And how are you going to solve for that voltage? Your only choice is you're going to have to walk another path, and you're going to have to walk through that. You have to walk through there. So maybe I'll use the same Ant-Man, but I'll have him go this way. Like that. So Ant-Man's final path. Man. Okay. Here we go. Ant-Man's final walk. He starts here. He comes down. You just grab the volts, right? It's 3 volts. We see a plus 3 volts. He comes around, he comes around, he comes around, he comes around, he comes up here. He sees a plus on the way in, and the volts is, well, that weird script V that we're using. That's the volts. He comes out, he comes around, comes around. Now he sees a minus on the way in, and the question is, what's the volts across the 5 ohm resistor? Well, we solved for it. Let's look at our table. It's a 6.48. So that goes here. Ant-Man's back where he started, that equals 0. And so that's not so bad. Let's see, what's that end up being? 3.48, I believe, because you add this on both sides, but you subtract this on both sides. So the voltage is equal to a 3.48. That would be the voltage across the current source, 3.48. I can shove that right there. And now we're done. And now it's time to take a break. Whew. So that was a pretty good workout, right? Pretty good 2 examples of stuff. Your homework is 2 more problems that you can do to sort of get used to this. And by the way, why are we doing all this stuff? Well, this gives you an idea how LabVolt works. When LabVolt is solving for things, somebody had to program it to do systems of equations and Kirchhoff's laws. That's how you program something to solve circuits for you. You use the Kirchhoff's analysis. So it's also darn useful if you don't happen to, you can, once you learn this, you can just bang out quick analyses. Hopefully they won't get quite this involved, but this, if it gets this involved, it gets this involved. You can do it. You can solve it. You have the power.